Alright, so we're going to discuss the period of a simple pendulum. So all a pendulum is a mass that's hooked to a string. That's all it is. So the period is just, so if, let's say the pendulum starts here. We can say that there's potential energy here, right? So let's say it hits a maximum point here, where it's also stored potential energy, right? This distance is the period. It's a full swing. So it's a full swing. And it's the time it takes for that full swing to occur. Alright, so now you know what a pendulum is and a period is. How can we calculate the period? Well, it's just t for time equals 2 pi. Alright, now we multiply by the square root of the length divided by the gravity in meters per second squared. Alright? So you may be asking why there's no mass in this equation. So if you remember Galileo, he did a famous experiment. So he'll take like a feather, yeah, it looks like I don't even know what it looks like. Let's just say that's a feather, and then he took a bowling ball. Right? On normal conditions, the feather would take longer to fall to the surface, the ground, and then the bowling ball would fall first. This is because of air resistance, which is just drag, which resists the relative motion of the feather. But let's say that we're in a vacuum. What will happen is this feather and the bowling ball will fall at the same exact time. So you could say that the speed at which a mass falls to the ground is the same for any object, minus the fact if there's no resistance. Okay? So mass doesn't matter because all objects fall to the ground at the same speed. And same thing occurs for this pendulum. Alright, so I have this metal, right? Metal, yep. So it's a pendulum basically. So I'm gonna find the period of the pendulum of this. So I measured this metal, and I found from the string, which is not really string, but like whatever. So the length of the string is 0.44 meters. Now, what is gravity? Well, it's just 9.807 meters per second squared, right? So if you take an object and you raise it a height and you drop it, every 2 seconds the object is going to be have an increased velocity of times 2. So in 2 seconds you'll have 19.6 meters per second velocity. Yeah, acceleration is just the change in velocity. Alright, so I'm going to do a bit of rounding because pi is a ridiculous number and I'm not going to go that far in. So time equals approximately 2 times 3.14 times 0.44 meters over 9.807 meters per second squared. Alright? So t equals approximately 6.28. Oh yeah, sorry, I forgot the square root. That's important. Times, so what's the square root of 0.44? It's approximately 0.663, I think it's 3 meters. Square root of 9.807, approximately 3.3 meters per second. Since you square rooted this number, the squared goes away. It gets canceled out. So now, if I'm just gonna do all the math because I did this math before, so it's just gonna become 1.33 seconds. This is an approximation, so it's not gonna be exact, right? So that's the full period from here to here or here to here. It doesn't matter either way. So I'm going to be back with the experiment showing you that this actually is the time it takes. Alright, so I have the pendulum here. So I'm going to hold it from here where potential energy is at. It's going to convert into kinetic energy. It's going to hit a maximum point of around here, where the potential energy is then converted back into kinetic until here. So I'm going to let it go from here to here. It's going to be one whole period. I'm going to do this 10 times so I get a more accurate representation, because that's how probability works. Alright, so I'm just going to start. This is about a 25-degree incline angle, as you can see. And I'm going to count the amount of periods, which is 10. Alright. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Alright, so I'm going to divide by 10 and show you. I'm going to show you the calculations again.